In this video, I'll talk about the integrated rate law. This integrated rate law tells us how the concentration of the reactant changes with time. So I'll talk about the zeroth order, first order, and second order reactions. First, the zeroth order reaction. This means the reaction rate, R, is equal to rate constant K times the concentration of the reactant to the power of 0. And this part is simply 1. Therefore, this R, the reaction rate, is equal to K, the rate constant. Both R and K have a unit of molar per second. Now, how do we define the reaction rate? Well, the reaction rate is the consumption rate of A or the production rate of the products. So let's go with the consumption rate of A. So this is the change of A. This is the time period. We put a negative sign here to ensure the reaction rate is positive. And by looking at this equation and R equals K, we know this delta A over delta T is equal to negative K. So this equation here. And then we have the change of A. The change of A is negative K delta T. Delta T is the time period. K is the rate constant. We put a negative sign here. And this reminds us the change of A, the reactant, is negative. And by looking at this, we know from the beginning of the reaction, that's time 0, all the way to time t. The change of time is t minus 0, and therefore the concentration of A decreases by kT after time t. So we have this equation for the zeroth order reaction. The concentration of A, the reactant, at time t is equal to the initial concentration of A minus kT. For example, if K is 0.2 molar per second, again, in this case, zeroth order reactions, the unit of K is the unit of R, and K is equal to R. And then I'll give you the initial concentration of A, which is 1.0 molar. After 0.1 second, what's the concentration of A? So we first compute the change of A over here, delta A, is equal to negative K delta T. All right, so it's negative 0.2 times 0.1, and pay attention to the unit. This second to the power of negative 1. Over here you have second, they cancel. So after 0.1 second, the change of the concentration of A is negative 0.02 molar. And then the concentration of A becomes 0.98 molar after 0.1 second. Why? Again, at the beginning it's 1.0. After 0.1 second, the concentration of A drops by this much. So 1 minus this, we get 0.98 molar. All right. Now let's look at the second 0.1 second. So between 0.1 and 0.2 seconds, A drops by another 0.2 times 0.1. This is K, this is delta T. Okay, between 0.1 and 0.2. The duration is the difference between these two numbers, that's 0.1 second. Therefore, A drops by another 0.02 molar. So after 0.2 second, the concentration of A becomes 0.96 molar, and so on. After 5 seconds, A drops by 0.2, that's the reaction rate constant in molar per second. In 5 seconds over here, so A drops by 1 molar. We say A is fully consumed. Now we have a zero concentration of A after 5 seconds. All right. So now I'm going to do everything on an Excel spreadsheet. So let's look at this. So we have K entered here. It's 0.1 molar per second. And I'm going to do delta T being 0.5 second every time. All right. So this is time from 0.5, 1 second. And then the last number is 5.0 second. And then I have the concentration of A here. This 1.0 is the initial concentration of A. And then I will have a column as the change of A per unit time over here. All right. And remember, this part is actually negative R, negative reaction rate. And because this is a zeroth order reaction, negative R is negative K. So therefore we have negative K here. The reason we do this is because now we know this delta A over delta T is a constant. It's negative 0.2. And over here, delta A is the change of A during that time period. So how do we get this part? Well, by looking at this equation, we know delta A is negative K times delta T. So over here, we'll have just negative K, this number, times delta T, 0.5 seconds. All right? So this is how we make this Excel spreadsheet. After 0.5 seconds, now what's the concentration of A? That's the initial concentration of A, so this number, plus the change. Over here, we compute the change here, it's negative 0.1. So B5 is this number in this cell, B5. D5 is this number, all right? So we have the change. And then we need to know how fast A is consumed during the second 0.5 period. All right, it's this number. This is the reaction rate and also the reaction rate constant. All right, they happen to be the same for the zeroth order reaction. Also, we need to put a negative sign here because, again, this A decreases. All right, and over here, again, the time period times the rate of the change. So in the second time period of 0.5 second, again, A decreases by this 0.1 molar. And by doing the sum of the previous concentration and the change, we get the concentration of A at the first second. And we keep doing this. One way to do this is we can just drag it down all the way down. All right, and then we have all those numbers. And then we can make a graph out of it. So over here, I'm clicking this graph. It shows me that the first two columns are used. So now I'm gonna just make the graph from scratch. So what you need to do is you select these two columns, and then you click Insert. Over here, select this Scattered. You can see this is a linear relationship. We need to label the vertical and the horizontal axis. So I'm gonna click this plus, and I'm gonna click this axis title. So over here, there's the time. The unit is second, and over here, this is the concentration of A. The unit is molar. All right, so we got everything. And then if you click this entire graph, I think we can change the font type to be bold, and now it's black. And then we click this plus again to get the trend line. So what we can do is we can select this linear, and you know it's going to be a linear equation. Check display equation on chart, display R squared value on chart. Well, this is just because we want to know what's the relationship between the concentration of A and time. So Y is the concentration of A, X is time. And now you can see y equals negative 0.2 x plus 1. This is actually the concentration of A equals negative k. This 0.2 is k times time multiplied by time, and then plus 1. This one is the initial concentration of A. So we have this relationship. And then let's get back to the document here. So this is what we got. Again, this is the concentration of A at time t, and this is negative k multiplied by time, and then plus the initial concentration of A. So initially it's 1.0 molar, and then after 1 second it's 0.8, 0.6, 0.4, 0.2, and all the way down to 0 here. After this y becomes 0, or after this concentration of A becomes 0, the reaction stops. So we stop here. All right, and I want to show you the equation again over here. That's the equation. This is the y. Time is your x. The slope is negative k. The intercept is the initial concentration of A. So again, once you get this graph, this slope is negative k. So k is 0.2, and this is the intercept or the initial concentration of A. Now let's work on the first order elementary reaction. So R equals K times A to the power of 1. And also we know this R is the consumption rate of A. So it's negative delta A over delta T. So this is how fast A is consumed. All right. And then by putting these two equations together, we have delta A over delta T is equal to K times A. So over here. And then we have this nice equation. The change of A is simply negative Ka times delta T. But this is not that simple, because this A changes. As the reaction proceeds, A decreases. So given the same time period, so let's say the delta T is the same, because A changes. So even within the same amount of time, the change of A is different. And because A decreases during the entire reaction, this delta A actually decreases as well. So how can we tackle this problem? Well, let's look at one numerical example first. Let's say K is 0.2 per second. Look at the unit here. Now the unit is second to the power negative 1. This is to ensure that the units on both sides of this equation match. Over here, you have molar on top, second on the bottom. Therefore, you have molar here. This K must be in this unit. All right, and then again, let's say the initial concentration of A is 1.0 molar after 0.1 second. What's the change of the concentration of A? Well, it's pretty simple. How do we get the change? This is the change of A. So we just plug in this K, we plug in delta T. Delta T, let's say 0.1 second, and let's pretend this A is a constant, 1.0 molar. Actually, it's not, because during this very short time period, 0.1 second period, although this is really short, this A still decreases slightly. But because the decrease is small, so approximately we're going to say, well, why don't we just assume this A is roughly a constant. It's going to be 1.0 at the beginning. It's going to be slightly less than 1.0 after this 0.1 second period. So we're going to say, well, roughly it's a constant. And that make the calculation easier. So we plug in numbers. It's going to be negative times 0.2, that's your K, times A is 1.0, times delta T is 0.1 second. And then we can tell the concentration of A drops again by 0.02 molar. The concentration of A becomes 0.98 molar after 0.1 second. Okay, now what's the difference between this numerical example and the example for the zeroth order? Okay, I want to emphasize here, this is an approximation. I assume that during this first 0.1 second, the concentration of A is a constant 1.0 here, although it's not. So this is a rough estimate. 0.98 is a rough estimate. All right. And now I'm going to show you the second 0.1 second period. That's between 0.1 and 0.2 seconds. All right. So A drops by 0.2 times. Okay, look at here. The concentration of A is not 1.0 anymore. It's 0.98 at this 0.1 second. So I'm going to use this number. All right. And then this is delta T. So now you can see this A drops by not 0.02 but 0.0196 molar. So it's slightly smaller than the drop of A in the first 0.1 second. Again, this is just because the concentration of A has changed. All right, so if we keep doing this, eventually you'll get this equation. It looks a little weird. We see this exponential function here, but after you take calculus, you will be able to derive this equation exactly. The concentration of A at time t is equal to the concentration of A at time 0 times an exponential function, e to the power of negative kt. So we're going to check this equation by looking at this kt. First, this kt is dimensionless. K is in second to the power of negative 1, t is in second, so there's no unit for kt. And 2, there's a negative sign here. That means when t increases as time evolves, this exponential function becomes smaller and smaller. What if t is infinity? When t is infinity, you are looking at e to the power of negative infinity, and that's 0. That means if you wait long enough, the concentration of A will become 0, or at least it approaches 0. So what if t is 0? Just plug in t is 0 here. E to the power of 0 is 1. Therefore, A is equal to A sub naught when time is 0. And that makes sense. When time is 0, we have the initial concentration of A. Therefore, it's just A naught. Again, A naught is the concentration of A at time 0. So we double-checked this equation with t equals 0 and t equals infinity. All right. So now let's see what does the change of A with time look like. Right. So this is a very large graph. So I'm gonna make it slightly smaller. This is how A changes with time. Okay. This is a exponential function. This 1.0 is A naught, and e to the power of negative kt. K is 0.2. This x is our horizontal axis, which is just time. Okay, and then y is our vertical axis, which is the concentration of A in molar. So at the beginning, it's 1.0 molar, and then after 10 seconds, it's here, it's 0.1 something molar, 20 seconds, 30 seconds, 40 seconds, 50 seconds. Well, actually at 50 seconds, this concentration of A is not 0. It's very small, but not 0. When does A become 0? You look at this equation, only when x approaches infinity. And then this y, or the concentration of A, becomes 0. And by looking at this graph, we can also tell how fast does the concentration of A drops to 50% of the initial value. The initial value is 1.0, 50% is right here. So we just estimate, actually it's roughly 3.5 seconds. And then from 0.5 to 0.25, well, actually it's going to be another 3.5 seconds. From 0.25 to 1/2 of that, which is 0.125, right? So it's somewhere here, another 3.5 seconds. So by actually looking at this graph, you understand it takes roughly 3.5 seconds to drop the concentration of A by 50%, regardless of its previous value. All right, so again, from 0.2 to 0.1, from here, this is 0.2. 0.1. 0.1 is here. So from here to here, okay, that's 50%. From here to here, that's actually 3.5 seconds. From 0.4 to 0.2, okay, this is 0.4, 3.5 seconds. How did I make this graph? Again, I'm going to show you the Excel. So this is the Excel. I entered this K here, 0.2. Again, pay attention to the unit. It's second to the power -1. And again, I'm going to use delta t equals 0.5 second. That's the duration of one time step. All right, and again, I'm going to do 50 seconds. So all the way down here, 50 seconds. All right, let's see. So this is time 0. The initial concentration is 1. And then I will use this number to compute the rate of the change of A. It's this one. Again, this is a first order reaction. So the reaction rate is K times A. All right, K times A. That's your R. And R, the reaction rate, is equal to negative delta A over delta T. So we have the negative sign here. And by clicking this, you can see how I got this number. $1 is this number. $1 means we'll always use the first row here. So it's going to be B and then first row. This way, I'm going to keep using this value of K. All right. Now the change of A. The change of A is simply delta A over delta T times delta T. Delta T is 0.5. So by using $2, I'm going to keep using this same 0.5 value in this same B2 cell. All right, so now that's the first row. Second row, I want to know what's the concentration of A at time 0.5 second. So what I do is I have the initial value, and then we have the change. The initial value is 1.0, the change is negative 0.1. So I'm going to use the initial plus the change, and that will give me 0.9 here. All right, and then now pay attention here. Look at this number. This is the reaction rate. However, over here, this reaction rate is different from this 0.2. It's smaller, only because now this A is smaller. So double click this, we have negative $1, negative K times the concentration of A. And now the concentration of A is 0.9, it's not 1. So because the concentration of A has decreased, the reaction rate decreases correspondingly. All right, so it's now negative 0.18. That's the reaction rate at this time. And then how much does this delta A change during this time period? Again, you have the time period times the rate. The rate is negative 0.18. The time period is 0.5. So again, I'm using $2 to make sure that this cell does not move down. All right, so we're not done yet. We have only 2 rows of data. But if you select this second row, you see this fill the square here. I'm going to just double click this square. It's going to fill all the way down. And then we can just make a graph here. So this is the graph of how the concentration of A changes with time. So we have A here, we have time here. And then in here, I used a exponential fitting. How do we do this? Click this plus sign and then go trend line. And then look at exponential here. Okay, select exponential, and then more option if we want to display equation. Okay, so I think what we need to do is plus over here, click more option. The default is linear, that's why you see a linear line here, but it doesn't fit our data. So we change to exponential, all right? And then you can display the equation. You can display the R squared value. So over here, all right? And now you can see this Y is the concentration of A, X is time. We're looking at just this concentration of A is equal to, over here, there's actually a 1 here. So that's the initial concentration of A, 1.0 molar, times e to the power of negative K times negative K multiplied by time. So again, X is time. R squared equals 1, that means perfect fitting. So really, by looking at this raw data, we see the reaction rate constant is 0.211. It's not 0.2. How come? Well, the reason is simple. Over here, I kind of assumed this A is just 1.0 between time 0 and time 0.5 second. But it's not true. Again, even the time duration is small. It's only 0.5 seconds. The concentration of A changes. It's not 1. Well, except the beginning of the reaction, it's 1. But when it's 0.5, you can tell it's not 1. So that's why we have some error here. And how can we reduce this error? Well, we can just think about it. How about we change the time duration from 0.5 second at a time to maybe a smaller duration? So let's look at this graph. In this graph, I changed the time step from 0.5 seconds to 0.1 second. So over here you can see we are looking at more rows. Why? Again, each time step is only 0.1 second. And then this is why we have actually 500 rows of data here if we need to go all the way up to 50 seconds. Alright, so that's 500 time steps. Each step is 0.1 second. But we do the equation just the same. So over here, this is just negative K times the concentration of A. And over here, that's the rate multiplied by this 0.1 second. And then over here, 0.98 is the initial concentration plus the change. The change is negative, therefore we get 0.98. But over here, you can see between time 0 and time 0.1, you can see the concentration is between 0.98 and 1. So that makes our approximation more accurate than the previous Excel graph. Over here, we assumed the concentration of A is simply 1.0. In reality, it's between 0.98 and 1.0, so it's not too bad. And now we just make the graph again. We get the same equation, except that this K now is 0.202. Okay, in the previous graph, it's 0.211. Now it's 0.202. Look at this K. 0.202 is fairly close to 0.2 now. All right, and then we can do even better. And you probably wonder, how do we do better? Simple. As long as we use a smaller delta t, we're going to get better and better and better. All right, when you take calculus, you will see the same thing again. So in calculus, we'll just use a tiny delta t to get the exact equation for the concentration of A. So you're going to see this later. All right, for now, what I'm going to do is I'm going to say, how about we just change this delta t to 0.02 seconds. So it's even shorter. And then we do the same thing. We use the same equation, except here. Again, I'm assuming the concentration of A between time 0 and time 0.02 is a constant. It's 1.0. So I'm making that assumption here. And this assumption is more accurate than before, because in reality, the concentration of A during this very short time period is between 0.996 and 1. So if the concentration is between 0.996 and 1, I think we can safely make approximation. Let's say it's just 1. And then this is the rate multiplied by the time duration. We get the change of A over here. And by adding up the initial concentration and its change, we get the concentration of A at 0.02 seconds. And then we keep doing this. All right. So we get, this time, I think we'll have 2,500 data points. All right, all the way down. Because again, we're doing 50 seconds. Each time step is only 0.02 seconds. So 50 divided by 0.02, that's 2,500 data point. So why did we do this? Well, now look at the new graph. Now we have like 2,500 data points here. Look at this equation we got. Y equals 1.000. That's the initial concentration of A times e to the power of negative 0.2x. X is time, 0.200. That's the rate constant. And by using this graph, we can easily find the concentration of A at any time, even beyond 50 seconds. So if I ask you what's the concentration of A at 100 seconds, you just plug in x equals 100 here. Okay, and then you'll just get 1.0 times e to the power of negative 20. Okay, e to the power of negative 20 is a very small number. Okay, and what if I ask you about time 100,000 seconds? You just plug in x equals 100,000, and then you'll see this y is extremely close to 0, and we can say, well, the reaction is complete. All right, so this is curvy because we're looking at a exponential function, and it's e to the power of negative kt, or e to the power of negative 0.2x, where x is time. This concentration of A drops exponentially. We call this exponential decay. Somehow it's a little bit hard to analyze mathematically. So how can we simplify this? We take the logarithm of both sides. So the logarithm of A is going to be the logarithm of A naught minus 0.2x, or minus kt. So that's what we did here. So over here, I'm actually using the logarithm of A, and we plot this with respect to time, and now it's linear. It has a negative slope. This negative slope is simply negative k. All right, so you see this equation. It's a linear equation with a negative 0.2 slope. That's actually negative k. Therefore, k is 0.2. This is actually how chemists determine the reaction rate constant k using experimental data. What about the intercept? The intercept is actually the logarithm of A naught, or the logarithm of the initial concentration of A. Okay? So that's the first order reaction. Let's get back to the document. I want to show you the linear equation here again. And then let's look at the second order reaction. R equals K times A to the power of 2. The reaction rate is also the consumption rate of the reactant. By looking at these two equations, we can equate this K squared and this negative delta A over delta T. It's right here. And then we can compute the change of A. Okay, the change of A is a negative number because the concentration of A decreases over time. And quantitatively, it's negative K times A squared times delta T. And then again, I'm going to use a numerical example. Again, this K is 0.2, but look at the unit. It's different. It's molar to the power of negative 1, second to the power of negative 1. Again, we have to balance the units. All right, it's called dimensional analysis. All right, so if you look at this side, it's molar divided by second. Look at this side, it's the unit of K times molar squared. So if you move this molar squared to the left-hand side, by dividing both sides by molar squared, you can see the unit of K is just molar to the power of negative 1 times second to the power of negative 1. All right, so again, we do similar numerical analysis, but this time we have this K A squared, that's the reaction rate, times delta T. We get the change of the concentration of A. It's negative 0.02 molar. So the concentration of A becomes 0.98 molar after 0.1 second. So it seems to be the same as before, but pay attention here. We are actually looking at A squared here. Again, this is second order. It's the concentration of A squared. Now let's look at the second time step between 0.1 and 0.2 seconds. Now you'll realize the difference. We have this A squared here. So the change of A is going to be 0.0192 molar. So what I did is I just used Google. I typed this up in Google to calculate this. Right? Again, you need to learn calculus to derive the exact equation of A in terms of time. So it's right here. So this is how the concentration of A changes with time. It's not very simple. It's actually the reciprocal of A at time t is equal to kt plus 1 over A naught. So that's mind-boggling. But again, after you take calculus, you will see this is the exact equation of how A changes with time. All right? So how can I convince you? Another Excel spreadsheet. Again, I'm going to use some fake data. I'm going to just calculate the concentration of A and see how that changes with time. And then you'll get a nice equation here where this Y is actually 1 over A, but just to remove the unit, I'm using 1 molar over A because A is in molar. If I do 1 molar over A, it's going to be unitless. All right. How about the horizontal axis against time? All right. And now you can see it's linear, and you can see the slope is actually, if you look at this equation, this is the Y, time is your X. So what's the slope? The slope is K. What's the intercept? The intercept is 1 over A naught. So really, over here, you see this K here, 0.2, that's your K. And this 1 is the reciprocal of the initial concentration of A. And then how did I get this? All right, let's look at this second order reaction. We have this K in a different unit here. Again, let's use delta T equals 0.5 second at the beginning. And then we're going to use smaller time step later. So this is time 0. This is initial concentration. Oh, I'm sorry. This is initial concentration. This is the reciprocal of A. So I put this 1 over A here, just make it easier for me to draw the graph later. All right, because later I'm going to use these two columns to make the graph. So this is concentration of A, and this is the reaction rate. All right. It's actually a negative reaction rate because the reaction rate is Ka squared. So what I'm doing is it's just Ka squared. This is our K times C5 squared. C5 is the concentration of A. So negative Ka squared over here. That's the reaction rate. The reaction rate times this 0.5 time period. We got the change of A during that time period. And then over here, this is the concentration of A at 0.5 second. It's the initial value of A plus the change. All right, we just keep doing this again, or we just click the filled square on the bottom right corner here, and we got the concentration of A. But again, we're trying to plot this 1 over A versus time, so this is 1 over A. 1 over C5 is 1 over this value, and then I'm gonna just click this square. I got 1 over A. So 1 over A increases as A decreases, right? And then the reason I put this column here because it's easier to just select data, and you can see what I did is I can just select all this data from here to all the way to the last row. Okay, so and then I made the linear fitting. This is linear, and I included the axis titles. I included the equation here. I included this r squared here. So this means a really perfect fitting here. And again, this slope is K, 0.204, that's your K, well, close enough. And this is the reciprocal of the initial concentration. Well, that's also close enough, all right? But still, we can do better by using a smaller delta T. All right, so this is going to be our smaller delta T. I'm using 0.1 instead of 0.5 seconds. And now you look at this graph. Of course, we need to produce more data. You can see there are many more data. I think there are 500 data points over here. But in this case, you can see the slope now is closer to K. The slope is 0.201 compared to 0.2, close enough. Also, this number is closer to the reciprocal of the initial concentration of A. So again, this equation tells you the reciprocal of A is equal to, again, this is K times T plus 1 over the initial concentration of A. All right, we have another spreadsheet. This time I'm going to use a even smaller delta T, 0.02 second. And again, I'm plotting this 1 over A versus time. The result is this. Again, the equation is 1 over A equals KT plus 1 over A naught. All right. So now this number 0.200 is the same as the value of K. And this 1.003 is awfully close to the reciprocal of the initial concentration of A. So again, you can plug in x equals 0 here. If you plug in x equals 0 here, this part disappears. You get 1 over A equals 1 over A naught. That's the meaning of this. That's the meaning of this. Also, you can plug in x equals infinity. What happens to this? X equals infinity, an infinite amount of time. So y is going to be infinity. And remember, y is the reciprocal of A. So if the reciprocal of A approaches infinity, that means A approaches 0. And that makes sense. After an infinite amount of time, the concentration of A is 0. All right? So we got those Excel graphs. So I'm going to give you some quiz questions about making the graphs, about analyzing the graphs.